Let's have a look at the other type of special series that we want to look at, the geometric one. So we had a look at arithmetic previously. Basically, it's exactly the same idea, but all I've done there is replace the word adding with the word multiplying. And so that's how this pattern goes. Instead of adding the same amount, we multiply by the same amount. And that same amount we call the ratio. So letter R. Now, if we want to find that ratio, we can get the second term divided by the first term, or we can get the third term divided by the second term, or just like we saw with arithmetic, we can get any term, in this case, divided by the previous term. Now, this also would allow us to create a recursive formula. If we try and make Tn the subject of that, there it is. Tn will be R times Tn minus 1. So that would be the recursive formula for geometrics. Basically, we're multiplying each term by whatever that common ratio is. So let's find a formula for it. Term 1's A, so the second term would then become AR squared, and the pattern starts emerging. Any particular term, AR, but 1 less in the power, so n minus 1. Now, if you were to plot these ones on a number plane, again, they're going to be discrete points, but these ones should form an exponential function. Because if you look at the general term, the variable, which would be x in the graph, is in the power. So therefore, we would be expecting some sort of exponential curve if we were to draw this one. All right, let's do a quick little example there. So 2, 8, 32 is the sequence. We're going to find the general term. So the ratio turns out to be 4. I mean, really, you can pick any term and do it by the one before, but I suppose I should just check it for at least 2 numbers. Because that division's 8 divided by 2 is 4. Remember, it has to be a common ratio. So I just want to double check, and oh yeah, 32 divided by 8, that's 4 as well. Let's plug it in. So 2 times 4 to the power of n minus 1. We notice that 4, hang on a sec, we can rewrite 4 as 2 squared. So we can come up with an even better formula here. 2 squared, apply the index laws, 2 to the power of 2n minus 2, tidy it all up, and there's our general term. 2 to the power of 2n minus 1. So if we were to graph it, what's it going to look like? Who remembers all their rules from shifting? It's 2 to the power of 2n minus 1. What have we done to our curve? So we've shifted it horizontally. How much? Oh, someone said 1, someone said a half. Which one is it? Yes, half. Remember, it's when it's grouped. So we'd have to factorise that. And if ever you're unsure, ask yourself what would make that equal to 0, because that's where the y-axis would go to. That's a half that would make that equal to 0. And I guess the 2 in front of the n, that's going to have an effect of making it steeper. Hang on, or shallower. Which way around is it going to go? I think it's going to be steeper? Shallow? Steeper. Okay. All right. Of course, it doesn't have to be the 2 consecutives, although with a geometric, we're going to have a little problem with this one. I've got the second term and the fourth term. Let's just work it out. AR would be 7. AR cubed would be 49. Simultaneous equations, but in this case, I'll divide to eliminate the A's. And we get R squared is 7. And here's my problem. So what's R? Plus or minus? I don't know. Because if it's negative, okay, I'll multiply by a negative number, term 3 would be negative, but then I'd multiply by a negative number, term 4 would be positive. So it might be positive, it might be negative. Unless they give me more information, I don't know. So I'm going to have to assume both. So the ratio plus or minus, without more information, I don't know. So that means the first term will also be plus or minus root 7, because I don't know whether it came from a negative number or whether it came from a positive number. So let's have a look at our general term. Well, I've done it for the positive case there. So it'll be root 7 times root 7 to the n minus 1, which is root 7 to the power of n. If I use the negative one, look what happens. It's similar, but I need to put that negative 1 to the power of n out the front to take into account the alternating. You know how we saw that in the sum notation and things like that? So if it is alternating plus minus plus minus plus minus, we're going to have in our formula negative 1 to the power of n, or n plus 1 or n minus 1. It depends whether you want the first one to be positive or the first one to be negative, what the power would end up being. What's the first term to be greater than 500? Because we've got 1, then 4, then 16. All right, so let's start that again. We're going to find our first term greater than 500. First term's 1, ratio's 4, so we'll get 1 times 4 to the power of n minus 1. Well, that just tidies up to be 4 to the power of n minus 1. We want to know greater than 500. So 4 to the power of n minus 1 is greater than 500. Two ways you could solve this: trial and error, and substitute numbers in and see what happens. But of course, a more efficient way of doing it is to log. Log both sides. So log of 4 to the power of n minus 1 allows us then, by our log laws, to bring n minus 1 to the front. So n minus 1 log 4 greater than log 500. Divide by log 4, and I get n minus 1 is greater than 4.48. Moving the 1 over to the other side. So I want the first number bigger than 5.48, which is of course 6. So term 6, which if you work it out, works out to be 1024. Now, just keep in mind, when you're using logs, the log of a number smaller than 1 is a negative number. So had I divided by, say, log of a half, then I'd have to change the inequality sign, because I'm dividing by a negative number. Okay, arithmetic and geometric means. The arithmetic mean is simply the average. Okay? And that's why in stats you often hear them just call it mean, but it's actually arithmetic mean. So add them all up, divide by the number of terms that you have. Geometric mean is for geometric sequences, and that's where you multiply them all together and find the nth root. I've put plus or minus there because if it was an even root, then just like we saw with the other one, you don't know, is it positive, is it negative? Odd ones will always be positive, of course, or always negative, depending on the numbers. All right, so we've got 4 and 25. If I was to say to you, what's the average of those, not a problem. If I was to say to you, what's the mean of those, then we have a problem, because are we talking arithmetic or are we talking geometric? Well, the arithmetic one, add them together, divide by 2, 29 on 2. Geometric, multiply them together, and we get the square root of 100, which is 10. So you can see dramatically different answers. But what it allows us to do with geometric and arithmetic series or sequences is it's a way of finding a term in the middle of two terms. So you use the geometric one for a geometric sequence, the arithmetic one for an arithmetic sequence. So if I'm told, here's our number pattern, 2xy 128, and I've got to find out what x and y is, and I'm told they form a geometric progression. So GP, geometric progression, which is the same as sequence. Now, I could use x equals the square root of 2y. In other words, the geometric mean. So x would be the geometric mean of 2 and y, so the one in the middle. And so x would therefore be the square root of 2 times y. And y would be the square root of 128x, because it's in the middle of those two. So we should be able to set up some simultaneous equations here. Y squared then becomes 128x, but we said x was root 2y, and so y to the power of 4 is quite a large number there, 32,768y. Factorise that, we get two possibilities, y equals 0 or y equals 32. Well, 0 is a bit ridiculous, because I don't know whether you realise this or not, but it's impossible for 0 to be a member of a geometric sequence. It's impossible. So therefore y is 32. Okay, I now know what y is. We can work out x by going back and working it out. So x is 8, and we have our number pattern. It goes 2, 8, 32, 128. So that's another way of doing it. I mean, I could have just gone back to AR to the n-1 and played around with all that, but it's possibly a little bit quicker depending on the numbers. Okay, so 1C and 1D. I've made a note there in 1D. Question 4. Try doing that one by using the idea of arithmetic mean and geometric mean.